So the acceleration is how fast our velocity is changing. So acceleration in this case is how fast the speed is changing. So at time t equals 0, we'll say the start of the race, their velocity is 0, right? But what the acceleration is telling us is that after 1 second, if it's a constant acceleration, then they're now going 0.4 meters per second. And after 2 seconds, if we're accelerating at 0.4 meters per second squared, that means we're accelerating 0.4, we're adding 0.4 to our velocity every moment. So that's 0.8 meters per second squared. And so you can extrapolate this, right? At t equals 100 seconds, then you'd multiply 100 times 0.4. So 0.4 times 100, that's 40 meters per second. They want the final speed to be miles per hour. But before we go on, I pulled this from a textbook that was trying to emphasize the fact that things don't usually keep changing at the same rate over time. Right? Maybe you could model a runner's acceleration by 0.4 meters per second for the first, I don't know, 5 seconds of a race or something like that, and then it levels off, okay? But 40 meters per second is wildly fast. We're about to see. If you're not sure what meters per second is and you're used to miles per hour because of cars, we'll make that conversion for you. Okay, so right now our units are 40 meters for 1 second. So we could write it like this, 40 meters for 1 second. So I went and got this conversion factor for us. 1 mile is 1,609.34 meters. So I'm trying to get miles per hour. I want miles in the top and I want hours in the bottom, right? So instead of meters, I want miles up top. So when I work with my conversion factor, I want the meters to cancel out, and I want 1 mile up top. So I'm going to put 1 mile in the numerator and this in the denominator. I'm dividing it by something that's equivalent, or at least approximately equivalent. That way, the meters cross cancels, and we have 40 miles in 1 times this is 1,609 seconds, because we still have seconds for our units in the bottom. Okay, but we want miles per hour for our final units, right? So we need to get seconds out of there. There's 60 seconds in a minute, and then there's 60 minutes in 1 hour. So there's actually, we want hours in the denominator, so I want 1 hour down here. And then we're supposed to put how many seconds are in an hour up top. That way we're taking something divided by itself. So 60 times 60 is what we want to do. There's 3,600 seconds in 1 hour. That way the seconds units cross cancel, and we've got the units that we were targeting. We got 40 times 3,600. That's 144,000 miles for 1,609.34 hours. And I think you can see where we're going with this, right? There's no way they could have been accelerating by 0.4 meters per second squared. So that's 89 miles an hour roughly, 89 or 90 miles an hour. Okay, so obviously people can't run that fast. Okay, so if they were accelerating at a constant 0.4 meters per second, after 100 seconds, according to that rule, they'd be going 89 miles an hour. So obviously something changed in there. Maybe they were accelerating at that speed for the first 5 seconds, but they surely couldn't be doing that the entire time. So, but that's the answer. That's how many miles per hour they'd be going if that continued.